Welcome back, everyone. You're tuning into the virtual forum spotlighting 2 decades of excellence, nurturing future leaders in STEM. This has been truly robust dialogue all day today. Now, our next session. His studies zero in on shelf processes, including coastal upwelling and estuarine connectivity, circulation in the Gulf of Mexico, and the interaction between physical processes and marine estuarine and ecosystems. Please welcome a distinguished research scientist, Dr. Stephen Morey.
Thank you very much. We're excited to have as an important component to the NOAA EPP MSI Education and Science Forum, a scientific program where students present their outstanding work. While we look forward to seeing a large number of CSC and other scholars present at the second in-person phase of the forum, we're excited to have, as part of the virtual phase of the forum, 2 sessions of scientific talks by Cooperative Science Center scholars. During the talks, please type your questions in the Q&A window and I'll relay them to the speakers. The first speaker today is Juan Carlo Cervera of the NOAA Living Marine Resources Cooperative Science Center and a master's student at the University of Miami. The title of Juan's talk is Development of the Southeast Region's Inland Essential Fishery Habitat Mapper to Inform Consultation. Juan?
Yes, thank you, Dr. Morey. Go ahead. All right. So thank you, everybody, for tuning in. Like I've already been introduced, my name is Juan Cervera, and I'll be speaking to my NERTO experience that I worked in collaboration with Dr. Jennifer Leo of the NOAA Southeast Fishery Science Center and Daniel Alvarez, a CMAS contractor who also worked with the Southeast Fishery Science Center. So let's see if I can get this. There we go. So I'm going to start off with a quick set into the basics of just essential fishery habitat. They're those habitats that are used to sustain fisheries through their life stages. You might consider this as, say, mangrove fringe, coral reefs, seagrass beds. It's really those estuarine and palestrine habitats that we see those fisheries sort of survive and sustain themselves through their continued life from larval to adult. And these habitats are protected under the Magnuson-Stevens Act, which requires that federal projects or projects that could cause undue harm to these habitats are done through a consultation with NOAA Fisheries so that they can understand to what extent are these harms being attributed. One of the ways that we facilitate these consultations is by using EFH web mapping. Now, this is really useful in being able to visualize these EFH bounds, especially for those project developers who may not be as informed about the different species that may be living in the area that they are working. And then also this simplifies the consultation process for the NOAA fisheries biologists who have to see these and say, you know, is this EFH, is this not EFH? And then also the project developers can come in a little bit more informed and say, look, we saw that this was EFH, and we just want to make sure that we're not causing any undue harm because of our project. Now, the problem arises with this when you start to focus in on some of those areas where you are going to see a high degree of projects, particularly in well-developed areas that get very complicated further inland. In this case, I'm speaking about the inland EFH mapping, where you have 2 cases here. One is you're going to want to have those higher resolution habitat extents so that you know whether you are actually within EFH or not, because the other possibility, and you can see that in the lower image, that when you have those lower resolution habitat delineations, you get a lot more artifacts that bleed into those areas that aren't necessarily EFH. So you're looking at these compromises versus sacrifices, and you have to know which one do we want to use. For the sake of our project, we really wanted to keep that accuracy. So we decided that high resolution has to be used because that would mean less unneeded consultations for the Southeast region. But how do you do this, and how do you get rid of those compromises that high resolution habitat extents bring? For the longer load times, we decided we're not going to load the layers, right? Now, this is for the sake of the personal computers of those users who can't load those really large and difficult file sizes of all these EFH extents. And then the other issue is those larger file sizes. You can have 10s, 20s, several different EFH species all within the same area, and having a file for each of them that has that high resolution gets unwieldy to keep on servers. So then what did we decide that we would do? Well, there was a certain logic, a certain process behind the GIS technician, Danielle Alvarez, how she was creating those EFH species extents, right? And the coding, which is what I was involved with, would take that logic and sort of translate it into a facsimile of what those certain species extents would be based on just a few files. This was the high-res habitat extents, the salinity bounds, and then the state and regional boundaries, so that we know which species are being protected, what habitat are we in, and what's the salinity that we're working with here that would facilitate those different life stages. So how was this done? The methods that were used for this particular mapping project in my side of things was using the JavaScript and Esri API. Again, we were using GIS spatial layers, so that's why we were using the Esri API. It's all within their private source. But then JavaScript is very open source, has a huge community support, and it gave me as a coder a lot more control over the widget variables and controls, the HTML visuals and functionality, and then those query and outputs that we were giving to the users as, you know, public entities, as those who may not understand completely the inner workings of both the application and the EFH consultation parameters. So speaking about my coding side, I did want to make sure that it's understood that this was part of a bigger portion of the development of this application. And it shouldn't be said that the coding was done within a vacuum. While it was completely possible that we could have made this application on our own, just between the three of us, it was very important that Dr. Leo had brought in these stakeholders to meet with us and give us this feedback consistently throughout the coding and development process, so that then as we were implementing, debugging, and designing the different concepts within this application, we would make sure that it was tailor-made for the stakeholders and then inevitably for the public to use. So what did the coding design look like? There are two main aspects to look at this. There's sort of the back end, or that function logic. Now, this is really where the code would create that individual species concept without add to the computations of the public user, right? We wouldn't have to add a different species for every layer. We wouldn't have to add the entire layer up to for the user to look at. What we could basically do is say, choose your location, is there EFH, and what can you expect from that EFH? And all of this is done in the background of the computer, while the tool logic, this is much more user-driven, and this is where you really need to get feedback from the users of the application. Because this is the point in time where users are going to be trying out the logic, and they're going to be saying, I want to do it one way. I want to use the latitude and longitude to choose my project area, but then suddenly say, oh, but I was drawing something. Now you have to remove that, right? You have to make sure that you are following along with how users and stakeholders are using your application. Which then leads into the implementation of the code that you just designed. This was very important that I took an iterative approach to this. The project lead, Dr. Leo, had used a sort of Scrum approach. You see it often with software development, where you sort of take an iterative approach and then you receive feedback and you do debugging. So in this case, you do the implementation very iteratively, you go step by step, and then the debugging is sort of a reaction to that iterative step. And you test it as you implement it so that you know where the bugs lie. And then you also know where feedback is best suited and where stakeholders want to put their feedback. Never go with unconsidered uses or never go with unconsidered inputs. Make sure that you are gaining that feedback all the way through the process. So how is the feedback broken down? For stakeholders, they're directly part of the development. In this case, that was the Habitat Conservation Division, where we were meeting regularly with them to test out the different code that we put in, that they could design different concepts. So, because this was really their application. This was for their sort of use through the public as they were receiving these consultations, and then they would give feedback into how their concepts were implemented into the code. And then communication was kept open with them as often as possible. Now with the public, they were brought in more towards a near finished aspect when we had an alpha and beta testing, and they could be brought in to say, you know, we don't have a direct concept design, but we know that I'm finding an error here. I don't like how this looks. I don't like how this works. But the public won't always give you those very specific concept designs. So you bring them in towards the tail end to sort of make it a tool that is easy for them to use and that they want to use, because that's what you want. You want to improve that information flow that you're providing to them through this application. So this is what it looks like. This was the finished product. It's up right now. You can just search Inland EFH Mapper, Inland Mapper on Google. It should be one of the first results. And you can see that you can't see the layers, right? And this is for that public user's sake. This is so that personal computers, phones, lower end products can still use this mapper without taking forever to load, get an answer back quickly, and be able to ask for consultations accurately without having to put the burden of high resolution layers on their computers. There's an example of how that high resolution determination works. This is a bridge leading to where I am right now on campus at the Rosenstiel School. And you can see when you click on the water, it tells you that it's open water. It knows that it's open water. It can give you a detailed list of all the species associated with Florida EFH for that open water area. But then if you click on the impermeable structure of the bridge, then it'll tell you, look, there's no EFH here, but still cautiously err on, look, if you need to, please contact your local EFH coordinator for the region, because it is important that we still erred on the side of consultation for conservation's sake rather than for, project sake, right? And so the afterlife of the product was making sure that the coding was all publicly accessible, that the data was all publicly accessible, and then that this could be hosted through an organizational GitHub. That's what we decided on in terms of hosting the code. And then succession of the code, I made sure, good coding design all the way through the practice. There's just very good spacing, well set programming blocks, and then making sure that commented often and that any future generation of programmers that take up the project can add an update to it when needed, and that updates are done regularly, that we always check on the project and we make sure that it is working, because really a project like this tends to have a life well after implementation and publishing. And then we just make sure that there's always some line of feedback from either the public or the stakeholders so that we can keep making improvements on it. And then I do want to speak to that this project was a remote success. We didn't go into this expecting that I would have to work on this remotely, but that happened to be the case. And it was still a success regardless, because a lot of the things that we were using was coding, developing, and meetings that were all able to be done remotely, right? And when we adopted a lot of software development processes that could be translated to this idea remotely. So that was one of the really big parts of this. And then also that we were already using existing data, and that everything, all the tools, the JavaScript, the Esri API were all freely available online. So I want to conclude with a sort of breakdown of what attributed to the success of this project, and hopefully that we could see more of these kind of projects in the future. But we considered what was available first, what was available with the data and what was available with the tools, and then able to sort of find that area where the data could have that marriage with the tools, with the programming, so that we could simplify it and make that very, very easy tool for the public to use. And then we made sure to always involve the stakeholders, despite everything being remote. That really, I felt made it easier to try and meet with people more often and build that application for their use. And by meeting with these stakeholders, we could cycle between my side of the coding and development and then their side of the feedback, and making sure that this project was built towards their end. And then finally, just keeping those avenues open for feedback and improvement. This is really important. We have that open for the public to come meet with us and, to bring that sort of, is it working for them? Is there problems that are popping up? Hopefully there isn't, but you have to be ready for that, because you can't anticipate everything. And then finally are the acknowledgements. So I wanted to thank the NOAA Fishery Southeast Regional Office Habitat and Conservation Division for funding this effort, and then as well as the NOAA Southeast Fishery Science Galveston Lab. They were kind enough to host my NERTO experience and bring me onto this project. The MES department and the Rosenstiel School of the University of Miami, And finally, of course, the NOAA Educational Partnership Program for hosting this, and it's very kind of you for hosting me as well.
Thank you so much, Juan, for that great talk. We do have time for a couple of questions. I do see some in the question and answer session, but I'd like to start off by asking one. Juan, for the audience that isn't familiar with the NERTO, could you please explain what that is and how it has benefited your academic career?
Sure. So the NERTO was really a facilitation for me as a student who may have not had any experience working in the NOAA lab before, to gain that chance to meet people from a NOAA office and sort of integrate some of my work and my expertise with their work and their expertise. And it's that combination and marriage of networking as well as getting a project done and having a feel for working with the NOAA project.
Thank you. And I see Chris has posted in the chat what the NERTO is. For those who are curious about it, it stands for the NOAA Experiential Research and Training Opportunity. And all NOAA Cooperative Science Center graduate students are now required to participate in this fantastic opportunity.
Yeah, right. Very good.
We have a question from one of the attendees. It's a technical question.
Okay.
And the question is that, well, you seem to have mentioned using the Java API code, the mapper. If it were possible to write the same code in a different programming language, such as R, where would you start to translate it?
So that is difficult to consider because R is much more of a functional program where JavaScript is a little bit more object-oriented. So R, I mean, you use it specifically for a lot of that statistical use, right? You use it for processing a lot of data, where the JavaScript was sort of using SQL database querying for that database use, and then using its functional or object-oriented programming for the tool use of HTML and stylizing the CSS. So it's hard to say how you could use R in this case, but I'm sure you could implement R into that querying side of things. But I'm not sure how you could use it for the sort of stylized side of things.
Right. Okay. Well, thank you so much, Juan.
Of course.
The next speaker today is Pamela Lara of the NOAA Cooperative Science Center in Atmospheric Sciences and Meteorology, or NCAS-M. Pamela is a Ph.D. student at the University of Texas, El Paso, and she'll be speaking about a NERTO experience, an in-situ investigation of the single particle soot photometer sensitivity with varying laser power. Pamela?
Okay. So this is a carbon study that I've been working on, and this carbon study has been done using a single particle soot photometer, or SP2, and 2 photoacoustic extensometers, or PACs. And what I'm going to share with you is my NERTO experience and how I was able to take that NERTO experience and pass it to my own research as a PhD student. This general outline of my talk today is a mirror of what I did on my NERTO and what I'm doing on my PhD research. I'm going to talk a little bit about the project, about the instruments, and about the focus of the work. So my NERTO, this was wonderful experience. I did it last year virtually, of course, because of the COVID, between September and December of 2020. And there I was fortunate enough to be accepted at the Atmospheric Composition and Climate Process Group, ACCP. There I worked with Dr. Joshua Schwartz and Dr. Joseph Katich. And the group itself was working with a campaign project together with NASA. And this campaign was called FireX. And so the group was divided, studying different parts of this FireX campaign together with NASA. Now, my project and the project that I was able to work on while on my NERTO was analyzing data obtained on August 8th of 2019. So the goal of my project was to be the efficiency or study the efficiency of the SP2 instruments in detecting the black carbon particles using different sensitivities on the currents of the laser. Our guiding question was, can we observe all the black carbon particles that enter the instrument? And here I have a little schematic of what is first for my NERTO, the single particle soot photometer. That was the main instrument. This instrument measure in situ aerosol. And in this case, the instrument was on board of a NASA DC-8 aircraft. And here on the left, you see sort of a general how the instrument look. In the center, you see a schematic of the function. So how this work, we have the airflow coming as the airplane moves in and out of plumes that comes out of wildfires, and the instrument collect the airflow, take it to a chamber. It has a laser at 1064 nanometers laser, and it pulverizes the particle through incandescence. So as the particle incandesces, we have different monitors checking that. We have a specific two monitor with filters. One we call the blue light, what we call the other one, the red light, and see this incandescence in with respect to time, with respect of the ratio of the incandescence. And here on the far right of the screen, and you see one of the graphs that I was able to produce analyzing this data. And this graph, though simple, it was very important to me. In blue, you see the black carbon mass. Now, the black carbon itself as a particle does not exist pure in the atmosphere, but it comes coating, it comes aggregated to other type of particles. So here you see the black carbon in blue that we collected. The red is just the altitude that the airplane was. This was north of Boise, Idaho. And there in the light blue or magenta color, I don't know what the color is called, you see that the laser was sort of dialed up or down with different changing in currents and milliamp currents. And the idea was to see, are we able to observe this black carbon when we dial up this current? And we focused the work in three important aspects of analyzing the black carbon. The first graph here, or the small graph there on the left, you see this graph that is showing the number distribution of the amount of particles that we were able to capture using these three different laser currents. We use it at 22, 27, and 3600 milliamperes. So we see a little shift on the red, that is the lowest setting on the laser current. And because it shifts from the main peaks, we can conclude then that at this lower setting of the laser current, we are missing the smaller particles. The other, at the center, you see a graph representation of what we call the BC color ratio. This is a color ratio because, as I mentioned in the beginning, we have a blue light and we have a red light, and then we take a ratio of both peaks. And this ratio is going to help us decide if the particles we are being heated up all the way to evaporation. If it's not, then something's happening. Then the amount of current that is going to analyzing the particle was not sufficient. And there on the far right, we see we are analyzing the coating thickness of the black carbon particle. So as I mentioned, the black carbon is not pure. So if this coating thickness is very thick or not, how that affects the study of the black carbon. Now, the super cool thing is that in my own research here, I was able to take what I learned on my NERTO and apply it, because I am a second-year PhD student at the University of Texas, El Paso, also UTEP. I am part of the Environmental Science and Engineering program in the field of atmospheric physics. My advisor is Dr. Fitzgerald. And my research study is the black carbon, but also brown carbon, characterization of these two particles in the El Paso Juarez airshed. So I was able to relate my NERTO with my PhD. So what is the UTEP project? So we have these instruments that we call the photoacoustic extensiometers, or PACs. We have two of them. One is the 405 nanometers PAC. The other one is that 870 nanometers PAC. And our goal is to observe or characterize the black carbon, be able to take from that black carbon the brown carbon, and to see if we can see the amount of black carbon and brown carbon that comes out of wildfires or biomass burning, because the black carbon has different sources, but we want to see the source as it comes of biomass burning in our state or outside the state. Our guiding question is, can we observe these traces of black carbon and brown carbon coming out of the wildfires here in El Paso and Juarez, since we are in the border? And we just did not use, or we don't not only use the PACs, but we also use other instruments. For example, the climate, which is a particle counter. We use the ceilometer because we want to sort of investigate how the planetary boundary layers and the rising and lowering of the planetary boundary layers is affecting the amount of black carbon concentration in the region. And also we use platforms such as the high split to check on the wind path. And so this is a general schematic of the extensiometer. Now, the cool thing is that this instrument is inside of our lab right now. I'm here on the lab at UTEP, and we connected to the outside through hoses. And what we do is the hoses bring into the PACS chamber the airflow. And the PACS has two chambers. One of the chambers analyze the absorption coefficient as the laser interact with the particle, and the other chamber analyze the scattering response, the scattering coefficient. And our focus work, so here I have 3 graphs for the same day. This is on December 6th of 2020. On the top here on the left, I have the total absorption coefficient, and we studied the absorption coefficient because black carbon, it is very important because absorb the sunlight. That is the reason that we call the black carbon also soot, because it's black, and this absorption is contributing to global warming. On the top, you see the total absorption coefficient coming out of one of the instruments, the PAC 405. And at the bottom, you see also the absorption coefficient, but this time coming off the other packs, the A70. And though the shapes are very similar, you see that the amounts, this is 1/length, are very different. And why is because on the 405, inside of this sort of like a total signal, we have embedded what is black carbon and also what is brown carbon. And on the A70 nanometers packs, all the signals that we see can be attributed to black carbon observation. So doing some mathematical gymnastic, we are able to extrapolate from the 405 signal what is exactly black carbon and what is exactly brown carbon. Here, I put a graph for the same day in the brown carbon. And at the end, we ended up with this kind of graphs. In black, for the same day, you see the net black carbon for that day using the PACS 405. In brown, you see of the signal what it belongs to brown carbon. And then here on the green, we see that of the signal what how the PACS A70 contribute. Because in theory, the black carbon, the amount of black carbon that we observe, well, the absorption coefficient of the black carbon that we observed using the PACS 405 should be around the same as the one that we observed using the A70 nanometers. But of course, you are hitting the particle with different energy. So the green is the A70, the black is the 405. They are not exactly the same because of these energy differences. So in conclusion, I loved my NERTO. I'm so grateful that I was able to be working with such quality, with such high quality of professionals, Dr. Schwartz and Dr. Katic. And the amazing part was, and I'm so grateful that I was able to bring what I learned about black carbon, even though it was other instrument, to my own research, because it's also involved black carbon. And I'm grateful for that opportunity. I think that it's going to help me keep growing. I learned several techniques to analyze the data. I learned to use some tools, for example, the Igor Pro that now I use on my own research. This very specific tool. And here I just want to acknowledge Noah, for the great opportunity that it gave me to do my NERTO. I have grown as a person. I have grown as a PhD student. I have grown also as a professional in the environmental science. And of course, to NCAS-M, to my mentors in NOAA, and of course, my advisor here at UTEP. Here are some of my references, and I'll be happy to take your questions. Thank you.
Thank you so much, Pamela. This is an excellent example of how your NERTO has really contributing as part of your PhD dissertation topic. Reminder to our attendees, if you click on the Q&A icon, you can use that to submit questions to Pamela. So Pamela, I noticed on one of your slides that you're planning on using the high split modeling tool, right? Can you tell us a little bit about how you're going to be using that? Do the soot particles, do they just simply behave as passive tracers when modeled with high split, or do they have some sort of falling, settling, or velocity or deposition characteristics?
Thank you. Thank you so much for your question. So first, the black carbon is only second to CO2 about affecting the climate change, in this case, global warming. And on the west coast of the United States, we have this huge wildfire season. So not all the wildfires happen here in our region, but that wildfire that happened on the west coast affect the whole globe. So we use a high split to trace the wind path. Did the wind bring all those wildfire plumes from the west coast to Texas? Are these the composition of the plumes that belong to black carbon affecting the atmosphere here in Texas? Now, black carbon is not only a global warming particle, but also affect your health. So through high split, as a tool, we are able to measure those paths, to follow those paths. We do sort of like a backward recreation of the wind to see where it came from, and also a forward recreation of the wind, because the black carbon, unlike the CO2 that stays in the atmosphere for a long period, the black carbon just stays in the atmosphere for weeks. So we have only this amount of time that we can trace where the black carbon is moving. And yeah, it moves through the atmosphere, the lower atmosphere, with the wind. That is the reason that we are using these other instruments, that is the ceilometer, because as the planetary boundary increases or reducing, we can see an increment of the volume or a reduction of the volume that we are observing of black carbon. Did I answer your question?
Oh, yes, great. Thank you. That's a great application of that tool. We have time just for one brief question here. And I'm sure several of us would like to know a little bit more about black and brown carbon, how they're different.
Very good. So black carbon, as I said, is a global warming, or is a particle that is affecting the climate, because there is something very important in the characteristic of black carbon, is that it is absorb the sunlight. That is the reason that is completely black. We call black carbon, or also known as soot. Now, the black carbon is only second to CO2, isn't it? But black carbon is not the only particle that comes out of a wildfire and CO2 that is affecting the global warming, but also brown carbon. Now, when you see a fire, first you will see the black plumes coming out. But then as the fire dies down, and if the fire is not too effective, and you see sort of a smoldering, now the plumes are not black, they are brown. And this coloring, this brown coloring, is because of the brown carbon. That is also a global warming, because like the black carbon, it absorbs the sunlight. And when it absorbs the sunlight, it heats up. And of course, this heat up also the environment. Thank you.
Thank you. Excellent explanation. I believe I noticed this at my house yesterday as they were doing a controlled burn in the area, and it looked like it was sunset all day as the sky had an orange hue. Thank you so much for that wonderful presentation, Pamela.
My pleasure.
Next, we will hear from Akisha Glenn of the NOAA Center for Earth System Sciences and Remote Sensing Technologies. Akisha is a PhD candidate at the City College of New York. The title of Akisha's talk today is A New Framework for Detecting and Forecasting Large-Scale Flood Risk in the U.S. Using Climate Information. Akisha?
Thank you. Let me share my screen. Okay. Thank you, and thank you for having me. So before I go into this new framework, I'm going to get into some stats about floods and the motivation for why we're even working on a new framework for detecting and forecasting floods. So you may have heard some of this earlier, but just in case you missed it, floods are actually becoming more frequent and intense in the US, especially over the past several decades. Unfortunately, more and more people are dying as a result of these extreme flood events. On top of that, you have more of these events crossing the $1 billion mark. So they're becoming more deadly and more costly. And this trend is actually projected to continue as climate projections are showing that we will be experiencing heavier rainfall events and more severe weather events. Now, how these floods are occurring actually varies greatly across the country. As you see here, the Northeast has quite a number of these floods. You also have the Southwest portion of the US, Texas. There's other areas sprinkled through in there. We know that recently Tennessee, unfortunately, had that large flood event. So this is ever changing, especially as we experience climate changes. So it's important to understand the distribution and the frequency also for flood risk management purposes. So how they're even predicted or mapped in the first place. So in the top left here, this is one of the common ways that we'll get a forecast. You'll get an alert on your phone, like, hey, flood flash warning or flood warning, flood watch. And that's within a few hours over the course of the day. Then you have the other end of the spectrum, which is the bottom left, way into the future. So 2050, 2100, as you see here, projections. But oftentimes the one that we see a lot is this one on the right, which is like this flood zone, floodplain style of map, often from FEMA. This is used for flood insurance and flood risk management. And often you might see it maybe at a state scale, mostly county scale. These type of maps are very common. Now, depending on your goals and what you are trying to forecast or understand, of course, each one of these predictions or risk maps have their place. There's benefits, of course, challenges to each, but for the most part, a lot of these maps are locally developed. So the focus just on that river or that stream in that location. And of course, if you see here, this is a map from FEMA and the other maps we just saw, there's this in and out kind of designation. So if you're in a county and it's red on the map and you live at the border in the neighboring county and you're like, well, I'm right here. Like I live right across the street, but I'm not a flood zone, you know, because you just didn't make the cuts for that borderline, how the county is broken up. So it can go the reverse way too. We can show that you don't have maybe flood risk and maybe you should be designated as a flood risk area. Then on top of that, again, with the locally developed models, sometimes there'll be missing information if there was no flood risk review there in the case of FEMA. So that's why you have gaps here. And then when they do have the information, it's kind of just pieced together to then put together this whole nationwide type of map. On top of that, climate changes are not really considered because of the time frames that you saw. Either it's like within a few hours, or if it is considered, it's way, way, way into the future. So there's that missing gap for like, what can we do right now? While we do have that long-term planning for climate changes for 2050 and 2100, what can stakeholders do in the short term to mitigate these impacts? from these extreme floods that we're predicted to see an increase in. So that's where the motivation came for this new framework. So what we aim to do here is, yes, we're still considering the individual stream flow information, the historical information, but instead of considering them individually, we want to see how they behave simultaneously. So we're trying to classify simultaneous flood events and use that as a way to forecast regional scale events. So in that way, you still have that regional view, but you're not restricted to this in or out, because each river, haha, that's like a hybrid of stream and river. I'm inventing new words here. But that's the information for the stream or the river is relevant for the drainage area for that region. So that's what we're aiming to do here, is try to leverage like patterns that we see when these floods occur at the same time. Now we're classifying these under this compound flood index. That's the name that we gave it, and open to suggestions, but that's where we're at right now. So the compound flood index, the CFI, is just the total number of these simultaneous flood events that the region, or the region that you're studying rather, is going to experience, but within a next season. So it's in between, not right now within a few hours and not 50 years from now, but what can you tell us if you know the conditions for this winter and use that information to predict the conditions for spring? So that's the idea here, is to use these compound events as your input for the forecast. So to demonstrate this and to apply and see if this even is reasonable, we look at HUC 2, and there we have 55 stations available. There's more, but these are the stations that start from 1955. And more importantly, these are unmodified streams and rivers. So there's no dam or man-made structures there, because we want to explain these changes based on climate information and don't want interference from like dam management or something like that. So overview of how this works. Now, say your season that you care about is January through March. Now, typically, as I explained before, each of these stations, you would just look at them individually and see, okay, this one had 4 floods during that time, this one had 3, this one had 10, so on and so forth, right? But what we're proposing with this compound flood event is how many flooded on the same day or at the same time. So for example, you have day 1, you have 2 that flooded here, 6 that flooded here, 4 that flooded here. But the CFI also takes into account how many flooding at the same time is a significant number, right? Because, okay, if you have 2, 6, 4, like how do you know how many flooding at the same time is actually something that can be explained? It didn't happen by chance. So that's what we're considering, these spatial extreme events. And for example, let's just say it's 3 or more. So those days that have 3 or more flooded stations are significant, and those would be counted into the CFI. So calculating the CFI, you would take your stream flow data for each of your stations, and you just need to determine if a flood even occurred there. So that's the benefit of this, is that you don't need to go in person per se immediately. Of course, there's some validation that needs to be done, but for the most part, data-driven approach. So you just determine from your time series if there was a flood. You can classify. What we did is we used the 99th percentile of the stream flow, and anything that exceeded that, we designated as a flood. Once you know when a flood occurred at each station, then you go ahead and see how many flooded on a given day. Then, as I just mentioned, you then can run some type of test. We use binomial PDF and ran some experiments to see what number of stations flooding was significant. In our case, it was 3 or more. And then you total those up to get your compound flood index value. So for HUC 2, for the whole year, there were actually over 1,900 of these simultaneous floods. And for the dominant season, when we did the climatology, if you see here from January to May, with a peak in March, there were over 1,200 of these simultaneous events. And then when we look at the time series, we don't necessarily see an obvious increasing or decreasing trend in the number of these compound events, but we do see some peaks here. And that's what we're aiming to explain now using that climate information. So just to look into what we're doing for the predictors. So we took the CFIs and we correlated them with sea surface temperatures and known climate predictors, right? Climate indices. And we were able to see that there was some that stood out. We have this dipole moment occurring here, and then also some possible PDO influence there, some SSTs off the southeast of Florida, and then of course, Nino 1-2. And the idea is to now take this information, the climate information, your CFIs, and make a prediction. So we did that. This is a preview of what we're aiming to do with these predictions. And we use KNN, nearest neighbors here. And the idea is to have a prediction that not only is in the right direction, which is if we say there's going to be a lot of these CFI events in the spring, then what actually occurred were there were a lot, and vice versa. If we say there weren't going to be a lot, and then what actually happened was, you know, there weren't a lot, like below the mean or median, that's the right direction. But most importantly is the regret score. And that is, we want to make sure if we predict that there are going to be a lot of these events, that that's what actually happens, because we want flood managers and stakeholders to be able to take our forecast and take some action to prepare them for the upcoming season. So we don't want to say, no, you're not going to have a lot, and then they end up having a lot of these events. We would regret that. So that's why we're saying regret score. And this is just a little demonstration. So the observed is the red boxes, and our predictions are the larger boxes here, and this one's shaded. So we have observed that fell within our prediction, so we don't have a regret there. But here we said, hey, you're going to have a lot of these events, and in actuality, there weren't many. It was below the median. So this is something that we regret, and these are the type of things we want to avoid with the forecast. But otherwise, yep, this is just an introduction to a new way to view floods, and actually we're able to classify them from this simultaneous perspective. And based on the model that we're using so far, we have some promising results that we're able to actually predict the number of these events for the upcoming season. And with that, thank you so much to NOAA assessors, my advisor, Naresh Devanini, and of course my NOAA mentor, Tom Smith. And yeah, that is it. So thank you.
Thank you so much, Akeisha, for talking about that wonderful work. In the chat box, Jen Leah wants to know which area had over 4,000 flooding events.
Oh, which station or which part? Mm-hmm. That's a good question. So that's something else we're also doing, is trying to do like a frequency of which stations are the ones that keep popping up. So we're playing around with some maps up there, but for the most part, the ones that seem to have a lot are more towards the northern part of that Hub 2 region.
Do you have any plans on extending this analysis to other regions?
Absolutely, yes. So we wanted to show proof of concept to see if there was even anything to this simultaneous occurrence. And yes, we've already worked on Hub 1, which is the rest of the northeastern US. And we're looking to extend it to the whole entire US.
Well, I look forward to seeing the results in the Southeast. Thank you so much, Akeisha. So the final student speaker today is Brianna Ramirez of the NOAA Cooperative Science Center in Atmospheric Sciences and Meteorology, also NCAS-M. Brianna is a master's student at San Diego State University. Today, Brianna will be talking about hybrid gridding for reconstructing maximum temperatures over California on a 1/10 degree resolution grid. Brianna?
Hello, everyone. Let me go ahead and share my screen. Okay. I'm guessing you all are looking at the screen. Perfect. Okay, well, thank you for joining us for the annual NOAA EEP MSI Education and Science Forum. As I was introduced, my name is Brianna Ramirez. I am in the cohort 4 NCAS-M. I'm studying my MS in statistics at SDSU right now. This is the project that I completed during my NERTO experience at the NWS office of San Diego under the guidance of Alexander Tardy. Let's go ahead and go on to some research overview. So my project was really technical. I'm kind of more of a data scientist than a meteorologist or anything like that, but I did get some really good background and interpretation behind this project, especially things surrounding Santa Ana events. That's kind of my focus on the temperature reconstruction. So our main goal was to create a full temporal field throughout the interpolated days in order to show the maximum temperature variance present during major Santa Ana events. One of our objectives was to generate a 1/10 latitude longitude gridded data set of daily maximum temperatures over California for most historical major Santa Ana events. We're doing this interpolation dating back all the way to 1895 using a hybrid method for interpolation. So eventually, once this research is fully completed, we will have a 110-year span video of California's daily maximum temperatures. So then you'll be able to really see the maximum temperature variation and look at trends and stuff like that. With the completion of this project, climate scientists will be able to visualize a full temporal and spatial field over California of temperature anomalies surrounding historical Santa Ana events. And here in California, it's an anomaly that plagues us yearly, and they do happen to be getting more severe as the years go by. So viewing and understanding historical climate data will be extremely beneficial for those climate scientists trying to determine the temperature trends over historical time periods. This type of work helps us understand the maximum temperature distribution throughout history in California, which can influence many climate-related policy decisions here. Okay, so data and methodology. I had to do a lot of coding myself for this project. It was quite tedious, but I did get through it. And now I just have a few more things to iron it out before I apply this algorithm to my master file that dates that 110-year span. But the data that we used in this project was collected from the Global Historical Climatology Network daily summaries, which is a database of daily climate records from numerous sources that have been integrated and subjected to a common suite of quality assurance. The spatial coverage of these daily summaries is global, and it is collected from over 180 countries and territories. The GHCN data collects on numerous variables such as maximum, minimum, and average temperatures, also a lot of precipitation, snowfall, stuff like that, and a lot of different attributes that are associated with these numerical values. Many stations do not collect all of the named variables. However, if a station resides within the same network, it can be assumed to collect similar variables. In my study, the station data that was used for interpolation and the error analysis that we ran with my gridded data sets was collected from the US Cooperative Network, the US Interagency Remote Automatic Weather Network, known as RAWS, and the Weather Bureau Army Navy Identification Network. Upon investigating the documentation of these networks, everything is kept in very wildly different formats. So I did have to, really read into the documentation of these data sets. I began the basic extraction of the station data for all the stations located within the California state borders. Then further extracted stations who only collected daily maximum temperatures. And in order to compile the 1,500 California station data sets, I was able to create an algorithm that compiled all of this data into one master file. This master file contains close to 2 million daily records and includes station records dating back all the way to 1860. And that's the reason why our final gridded product is going to be interpolated between 1895 and 2005, because all the data before 1895, it's really, really scarce. And even in like the early 1900s, we're going to have like really wild estimations for maximum temperature, because we're going to be estimating really hard, like interpolating like on interpolated data, So it does, have a grain of salt when you're going back to those like really early dates. For today's presentation, we only utilized the data gathered from October 2003. This was a major Santa Ana event that happened in California. We chose this one because it was preceded within an extreme heat wave. So we wanted to observe our final graded product looking at this heat wave that preceded this Santa Ana event. This visual that you see is depicting the 1,500 stations that are used in this study. A little more on the methodology of this. Our method for interpolation is called the hybrid method and is a blend of two simpler methods, namely inverse distance weighting and nearest station assignment. IDW is calculated by collecting daily maximum temperature data from all of the stations within a 50-kilometer radius from each of those grid points that you saw on the last slide. So once you collect all of that data that's within a 50-kilometer radius, we then interpolate it to each grid point by this really complicated IDW formula, which uses the daily station data, the Euclidean distance between the station and each grid point, and then we just sum it up and basically raise it to the negative first power in order to get an IDW calculation for each grid point on each day. So basically, we are breaking up California's grid into a 1/10 degree latitude longitude grid, and then interpolating for every single point every single day. This, as you can imagine, takes a huge amount of computing power, and that's actually one of the things we've been trying to wrestle with, trying to optimize some of my algorithms so then we can apply it to the 100-year span and actually get like a live movie of maximum temperature variations to go on. A little more about IDW. It is a smoothing technique which allows us to calculate the monthly total of a grid point from each daily station. The nearest station assignment, the NSA method of interpolation, assigns the nearest temperature maximum value to that grid point. The NSA gridded product is a high resolution temperature maximum grid following all of the spatial patterns that are present in our observations. Estimates though from the NSA method tend to be a little bit, rough, because the nearest station may not be within 100 kilometers of that grid point, or in California it has vastly different terrains. So you could be estimating for a grid point that's, nowhere close to that actual temperatures that are happening there. So the hybrid method is a blend of IDW and NSA, and the main function of the hybrid equation is to distribute the monthly total maximum temperatures obtained by IDW to the daily maximum temperatures dictated by the station data. Basically, overall, IDW overly smooths the spatial distribution of max temperatures, NSA roughens the spatial distribution, and the hybrid method allows NSA to update the IDW calculation and creates a really good middle ground that considers the monthly trends as well as the nearest station. My gridded products for all show a full temporal field over California. This picture is for October 21st of 2003 and was reported to have the highest average maximum temperatures. So it shows the maximum temperature distribution the best. We can see that the IDW up here smoothens out the observational values, especially in the Southern California region, where you have a lot of stations going into that data. NSA has a really rigid distribution. So, these areas where you're not collecting too much data, that's really not accurate, because look at how little stations we have over there. And those little stations are estimating this huge amount of area, especially in the Central Valley region. And then finally, we have our hybrid method right here, which is the IDW that's adjusted by the NSA. And we do get a more complete idea of the temporal variance that can happen in different parts of California's terrain. So this is the hybrid product for October 2003. I'll go ahead and play it. It captures the monthly variation in station sparse areas and provides a more complete field over temperature maximum in these areas over other methods. Overall, we do see the hybrid data set catching small nuances that were not picked up by the rough NSA method or the overly smoothed IDW method. We did have some challenges and issues that went along with this project. As I said, my IDW calculation, it wasn't exactly optimized for such large computing. We're trying to run this for 100 years, and this 1 month span took about 2 hours to run with the algorithms I created. Unfortunately, I am not a data scientist, but I have been working with a few great people from the SDSU Climate Informatics Lab, and they're helping me iron out some of my algorithms I created for this study. I have explored the ideas of using multi-layered pipelines for computing the IDW calculation. I think that's the one that's kind of slowing everything down. So I do need to revisit that before applying it to that master data set. Another thing that we were going to consider when we optimize all of our methods is that we might use a distance measure that considers elevation, because California has vastly different terrains, and we have lots of mountains here if you've ever visited. And so having a distance measure that considers elevation as well as the direct mileage between each grid point and the station, I think would make our measurements much more accurate because of the elevation changes that could happen. In the coming future, I will continue to work with the climate professionals at the NWS office of San Diego in order to further this research to the entire master file, which will eventually produce a full temporal field of California between the years of 1895 and 2005. I'd like to thank the National Weather Service of San Diego, more specifically Alexander Tardy, for his inspiration and continuous support in this project. I would also like to give a special acknowledgement to my advisor, Dr. Samuel Shen, and his continued guidance and advice on completing this research. Lastly, a special thanks to SDSU Climate Informatics Lab for their assistance in different areas of this project. And of course, thank you to everyone associated with NOAA NCAS-M. I learned so much from my NERTO experience, and I feel like I've really grown as a data science professional because of this project. Thank you for listening. With that, are there any questions?
Thank you so much, Brianna. That's a great tool, it looks like you're developing. There was a question wanting some clarification on how the weighting for the distance between the station and your interpolate grid point is used in your methodology. I believe that's in your inverse distance weighting function, but it looks like there are two methods being used. Is it used in the nearest neighbor approach as well?
So our inverse distance weighting, so we do end up weighting the different, because we're summing over that 50-kilometer grid. What happens with the weights is we're attaching weights by the Euclidean distance. So if a station happens to be super close to a grid, that's going to have a really heavy weight. And so I know I didn't put the equations up. I got some advice and they told me not to, and they were like, you're going to get way too much into the math if you put the equations up. But in those equations, the nearer stations, the stations with the least distance between each grid point, they do get higher weights. So they are going to be like the leading contenders that make the grid point Tmax value, at least for that IDW calculation. When we combine it with the NSA though, the near station assignment, it does almost like, I don't know, lessen the weight from the IDW because, you know, we are trying to look and consider the monthly variation, which is solely picked up in the station data itself. So we do kind of re-roughen our spatial distribution with the NSA because the IDW like really smoothens it down because it considers so many stations for one grid point.
Okay, great. Thank you so much. And there's no other questions. So thank you, Brianna. This concludes the invited student talks for today. We look forward to hearing from more students and alumni tomorrow. I believe that now there will be some poll questions posted as we transition to the student workshop.